How you guys doing? Okay, so I have some stuff here. You know, I really like old physics equipment. And so you find stuff and then you try to figure out what's going on and you try to figure out what it does and it's a mystery, right? And everyone loves that mystery. Okay, so here is this old CENCO electromagnet. We have actually a couple of these. And there's a bunch of accessories to go with this. So I'm gonna go over some of the demos, and I didn't find everything. So here's the magnet. The first important thing to point out is that it has two connections right here. You can hook it up to a DC source, or check this out. There's a plug and two wires. I mean, don't plug this thing in, okay? Yeah, it's not grounded, and then you just have these two free wires. So you connect these two things here, you plug it in, and it makes an alternating current in here. A couple of other features: it has a mount point for some accessories. It has an iron core that you can raise and lower. It's pretty awesome. Okay, so these are some of the things that I have with it. I have this thing. I have this ball, which I may or may not show you. Rings. This thing, I figured that out. This is pretty cool too. This is the one that it took me the longest to figure out what the heck this was, but I did. And then I actually found something like this. Check this out. Operating instructions. From what year? Doesn't say. But this stuff's old. Okay, so let's take a look at some of these experiments and see if we can get them to work. It'd be fun. You know, and sometimes we like to make a new little twist on things to get it to work, but let's just go. Okay, so this one's a classic demo. Oh, did you see my Team Tree shirt? Check that out, Team Trees. Okay, so this one's a classic. We're just going to turn it on. We're going to see if it works. I'm gonna connect this up. I'm not actually sure that this came with this, because as I connect this thing right here, it doesn't quite fit, but that's fine. And now you would just plug this in to turn it on, and that's kind of crazy. So actually, I have here a little power strip. So I'm just going to plug it in right there, and then I can turn it on and turn it off. Okay, so the first thing, there was actually this coil of wire with a light bulb on it. I don't have that. Well, I actually do. I broke it though. Actually, there it is. Let's see. This is the coil that came with it, but it's broken. There's a wire that's loose, and I gotta fix it. So let's just use this, a modern version. So this was actually a speaker I made, and so it has magnet wire wrapped around it, and I put an LED up there. Now this is going to oscillate back and forth to make electric current go back and forth. Which makes an oscillating magnetic field. That magnetic field induces a current. The changing magnetic field induces a current in the coil of wire, and that current will light up the LED. So let's see if we can get this to work. Turn it on. There you can. I don't know if you can see that there. See, it's on. And this is actually turning on and off because the LED only functions one direction of current. It's a diode. Okay. So there's your first demo. Okay. Next demo. So the first thing I did was I raised this iron core up a bit, and then we have this. This one's the most famous demo for this thing. This is called the jumping ring. So what happens is you put this aluminum ring right here, and when this is the same as the light bulb, the only difference is it generates a higher current in here because it's thicker. It's a lower conductivity, lower resistance, higher conductivity. That induced current makes an electric current in here that makes a magnetic field. That magnetic field pushes in the opposite direction of the change in current, and it shoots up. Let's just do it. Okay, you ready? Turn it on. I move my switch over here. Pretty cool, huh? Okay, what if I change that to copper? It's the same size. Okay, it's about the same size. The copper doesn't go as high because it's a lot heavier, but it actually has a higher conductivity. It has a higher current. This is the one that I read in the thing that I didn't really quite get to work, but they say you put this right here, Okay, and get that to hover. Now put the aluminum on there. They attract, and they get hot, actually. So what happens is they both induce a current, and they both make a magnetic field, and they attract each other. So they're being repelled by this, but since they have current in the same direction, they want to attract and stick together. So. Okay, next demo, it's this levitating plate thing. So this is a copper plate, and you put it on this mount point right here. It should go down further. Oops, I took the screw out. I don't know why you even need a screw. Okay, well that's fine. So you see, actually, there's a line on the other side, but that's fine. Okay, I'm going to turn it on. Let's see what happens. So, same idea. This induces a current in there. That current makes a magnetic field that repels, and it levitates. It also gets hot. Pretty cool. Okay, I have not tried this one yet. But these are one of the things that you find in the stock room, and it's like, what the heck is that? It's this copper donut with a little hole in there and a mounting point. You're like, I don't even know anything. So this is what it does. You put this over the core, and you tighten this up like that. Okay. Now, same idea is that it will induce a current, and that current will heat up the copper. Inside of here, there's water, and it's supposed to boil that. I don't know if this is going to work. Okay, let's just do it. I don't know how long it takes either. I could be sitting here for a while. It's hot, but it's not super hot. I'm not gonna let it boil all the way because I'm just too bored. Okay, but that's what that do, and then you can see the steam coming out of here. This is essentially how an induction oven works, right? You put that metal pot on top of a changing magnetic field, and it induces a current that gets hot. Okay, so you can also put the coil on its side. It actually has a little bumper down there, so you can see what happens. And I found this thing, and when you first find this, it's like, what? I have no idea. Okay, so but this mounts right here, just like that. And then I have this ring. And now this experiment, I think, is actually supposed to be done with a DC current hooked up to the coil, but I don't want to do that. So I'm just going to turn this on. Let's just see what happens. Something maybe cool will happen. So now I can take this ring, I can put it over there, and I can connect these up here. It's not even long enough. It's too long. Okay, well, the idea would be that you could hover this and turn on when you turn on the DC current, it should move out because of the changing magnetic field and then come back. I think in this case, it'll just kind of shoot out. Let's just do that. Yeah. But the cool thing is, once you do that, if you measure the angle that the ring hangs, you can actually calculate the magnetic force on it. That's pretty cool. Okay, there's one other experiment. I don't have all the pieces to it, but this is one of those things I'm like, again, what the heck? So this is part of a motor. So there's actually a spinning disc that sits right there. Not this disc. It looks like that. It sits right in there, but doesn't touch. And then you pour mercury in here to make an electrical connection. And then you apply a DC voltage through this and a DC voltage through that. And I think it makes something similar to a homopolar motor. But that's what that is. I'm not going to do that one. So, okay. I think I'm done playing with this. There you go. Okay, this one I have not tried also. It's this spinning ball. Don't know if it's going to work. Okay, so they say take a copper plate and put it on top, and then put water on top of that. I know you're thinking this isn't going to work. I agree. And then you put the ball in here. Okay, let's turn it on. No. Oh, I think it's leaking. I have a leaking ball. Okay, that's going to be a problem. Okay, so I'm not really sure how this works. I have a different ball right here, but it's cracked. So I don't want to put that in there. It will definitely... And I don't understand why this plate has to be there. So let's just try it like this real quick. Nope. Okay, that one didn't work. Okay, this is one that I couldn't figure out. I mean, I saw this in the stock room and I'm like, what the heck is this? This is aluminum and it's got a bottom to it. Now what gave me the hint that it went with this was this mounting point. You see it fits perfectly right there. So I couldn't figure it out. I looked inside and you can see some oxidation. I figured maybe some water went in there or something. I just really couldn't figure it out. Don't put water in here because it leaks. This is actually not aluminum. This is steel. And there's it doesn't really seal very well. There's a little crack right there. So I poured water in there and it just went everywhere. So let's just turn this thing on and I'll show you what it does. Okay, right there, that's good. Okay, I'm gonna turn it on. It's not that exciting, huh? So what happens is this makes a magnetic field that oscillates this metal on the bottom and it makes a noise. Now, I think it said if you get it at the right frequency, it will resonate with this tube. Well, and you can make it howl. So I didn't try that. I think you need a different frequency for that though. But don't put water in this. Okay, so let's go over the physics of how this works. I'm going to try not to get in the way of the camera. So the key here is this coil, the electromagnet. And the way I use this, I have this plugged into an outlet, which is an alternating current, and that's key. Okay, so now, two important things about electric fields. First is this. If you just have a single point charge, you can make an electric field that radiates in all directions. That's the way you normally think of an electric field. Well, no one normally thinks of electric fields like that. But that's just the first way that you can think of it. However, there is indeed another way to create an electric field. If you have a magnetic field, we use the vector B for the magnetic field. If you have a magnetic field, and that magnetic field is changing, then you'll make what's called some people call it a curly electric field. This electric field radiates in all directions. A curly electric field kind of like makes a circular path. Okay, at each point it's in one direction, but if you can follow it around, it's in different directions along that circle. So you need a changing magnetic field also makes an electric field. Why do we even care about electric fields? If you have an electric field, a curly electric field inside this ring, that electric field is going to push electric charges and make an electric current. So the electric field makes an electric current. Okay, so if you want, this is my version of Faraday's law. This is just the more advanced version. This is the path integral of electric field around that circle, and this is the change in the magnetic flux through that area. But if you want to see that. So in this case, what's happening is I have electric current coming into the coil through these wires, and then it wraps around and it makes a very strong magnetic field that goes up. And then that does not create a curly electric field. It does not induce a current. But then, because of the way we have outlets that have changing current, that magnetic field then goes down. It goes from up to down. That changing magnetic field is what induces a current in the ring, and then that current in the ring also makes a magnetic field, and that's where most of these properties come from. It heats it up and stuff too. So that's your very basic physics of what's going on here.